Okay, good morning again. I'm going to give an introduction to density functional perturbation theory with particular reference to the calculation of phonons and related quantities. My presentation will be a little bit formal, but I try to make it clear what all those formulas mean and what you can do with those. I'm not sure how to, sorry, trying to remove one icon in an inconvenient place. Okay, so this time I'll try not to be too long. I have something to do at 10:30, so I can't actually. Okay, so the summary of the lecture, but actually I guess it's not needed to introduce again density functional theory since you are here. You have already heard in the two preceding days about density functional theory. What is I want just to recall, because it's important for the rest of the discussion, is the form of the DFT energy functional, which is written as a sum of the kinetic energy of interacting electrons plus an external term, a term of interaction with an external potential, plus a Coulomb-Hartree term, so-called, and finally the exchange correlation energy. Now, this, let's say, we know how to solve this problem, we know how to solve it for a given potential, for a given external potential. So for a given, basically for a given configuration of nuclei and the corresponding potential or pseudo potential acting on electrons. And here is a summary of the technicalities that you are already aware of. Now the problem is, the problem that we want to deal with today is how to, what can we say if in the case of in which the external potential, so the bare potential acting on electrons in DFT depends upon some parameter, lambda, let's say, and where lambda equals 0 is typically our ground state, starting point, and we want to consider small lambda expansion. So we write the potential as a function of lambda, as an expansion of a power of lambda. And there will be, for sure, some equivalent expansions for the corresponding energy, the corresponding charge density as a function of lambda, and the corresponding energy as a function of lambda. So we want to figure out what are the derivative of the energy. In particular, we're interested to the derivative of the energy with respect to this parameter lambda, which in practice will be nuclear position or displacement around the equilibrium position or an electric field. Now, so what are these first order derivatives? In particular, the second order derivative, which is important because it's what we want to compute, because it's what determines the vibrational properties of the system, for instance. And how are those derivatives of the energy related to the derivative of the charge density, and how to compute the derivative of the charge density. Now, the first order derivative of the energy is quite straightforward, because we know that there is the equivalent of the Hellman-Feynman theorem for many Hamiltonians that holds for DFT, and so the derivative of the energy with respect to some external potential, to some external parameter, is the expectation value of the derivative of the Hamiltonian in the Hellman-Freiman theorem with respect to lambda. And in the FD, we can write the explicit derivative of the energy as a function with respect to the parameter lambda, the expectation value over the ground state charge density of the derivative, the explicit derivative of the external potential. All other terms vanish. And in general, this is, by the way, what we use to compute forces acting on nuclei. And in general, it can be shown, it's quite relatively straightforward to show that the 2n+1 derivative, the derivative of order 2n+1 of the energy depends only upon derivatives up to order n of the charge density. So in particular, the first order derivative does not depend upon the derivative of the charge density. This is known as the 2n+1 theorem. Now, the problem is what shall we do for the second order derivative? It's not difficult to write down what is the second order derivative, which depends only upon the first order derivative of the charge density. And there is a term that looks simple to compute. This term in the expression, the term on the right hand side of the rightmost term is actually quite straightforward to compute because it doesn't depend upon the derivative of the charge density with respect to lambda. And then there is this term, the intermediate, the term in the middle, in the expression here, which contains the first order derivative of the charge density. Now, this result can be generalized to the case in which there isn't a single parameter, external parameter lambda, but there are more than one. The surprising fact is that while one of the two terms at the right-hand side of the equation is clearly symmetric with respect to the exchange of the derivative, the other one doesn't look like it is symmetric, but actually it is. It has to be necessarily so. So once we have the so-called linear response, that is the derivative of the charge density with respect to lambda, we can compute the second order derivative of the energy. Now, how can the derivative, how can the linear response computed? One way to compute the linear response is the following. We write explicitly the second order derivative of the energy with respect to lambda square as a functional of the first order derivative, the first order linear response. And we minimize this functional. It has to be has to give the linear response because the functional of the energy is minimized at each value of lambda. So the second order derivative, the second order term is also to have a minimum corresponding to the linear response of the charge density. And that's one possibility. An equivalent possibility, an apparently different way to proceed, but actually equivalent because the basic ingredients are equivalent, they are the same, is to use perturbation theory and the self-consistent procedure applied to the Kohn-Sham equations. So what we do is first of all, we write the linear response of the charge density in terms of the linear response of the Kohn-Sham orbitals. And so first equation number one. And what is, how does the potential change, the Kohn-Sham potential change? The Kohn-Sham potential changes via a bare term, the explicit derivative of the potential, the certain potential with respect to lambda, plus a term coming from the linearization of the Hartree potential, and a term coming from the linearization, the linear response of the exchange correlation potential. The latter equation 2 can be written as, must be written as a functional derivative of the exchange correlation potential times the derivative, the linear response of the charge density. It looks complex to compute, but at least for reasonably simple exchange correlation functions, it's not difficult at all to compute the screening term, in particular including the exchange correlation screening term, the last term on the rightmost term on equation 2. Now, here we are assuming again the simplest case of non-magnetic insulator, so the sum runs over occupied valence states. Now, we are still missing this linear response of the Kohn-Sham orbitals, which you can compute using applying perturbation theory to the Kohn-Sham Hamiltonian, and perturbation theory that typically includes sum over unoccupied virtual states, but the sum over unoccupied virtual states can be rewritten as under the form of a green function, 1 over the epsilon v minus the Hamiltonian, acting on the perturbing potential, which is the screen potential, the derivative of the Kohn-Sham potential with respect to lambda times the Kohn-Sham orbital. The sum is over conduction bands only, conduction states only, so this is why there are these projectors over the empty state manifold. So the perturbation doesn't change valence, the perturbation that mixes inside the valence manifold wouldn't change anything. So in order to have a change in the valence Kohn-Sham state, you have to include a contribution from unoccupied states. Now, so this is the so-called Sternheimer approach, and the above equation, so the sum over the perturbation sum that is needed for perturbation theory can in this way be recast. The Sternheimer approach, known since many years in atomic physics, can be recast into the solution of a set of linear systems. So finally one has a perturbing term and a linear system to be solved that produces the linear response of the Kohn-Sham orbitals. But in turn, the linear response to Kohn-Sham orbitals enters the linear response of the charge density that enters in the linear response of the potential. And so this defines this set of equations, this set of 3 equations, 1, 2, 3, defines a self-consistent procedure in which instead of diagonalizing the matrix, we solve a linear system. By the way, in the approach the approach I mentioned before, consisting in expanding the density functional and minimizing it, what we do is basically the same, but instead of solving one problem per Kohn-Sham, one linear system per Kohn-Sham state, we solve self-consistently, we solve a big linear system for all Kohn-Sham states altogether. In the end, it's quite the same. So just a few remarks. First of all, so the projector of a conduction state is actually needed only for numerical stabilities, because if you mix valence states, the valence state manifold, nothing changes, but numerical stability is needed to get rid of those contributions. In fact, notice that this one over epsilon valence minus Hamiltonian, Kohn-Sham Hamiltonian would be singular on psi v, on states, on valence state. But it's not needed to have the knowledge of the conduction bands, which would be very inconvenient, especially in a plane wave pseudopotential approach, because conduction band is something that is typically not computed, or it's computed only around a small region around the Fermi surface. But one can simply write the projector of a conduction manifold as 1 minus the projector of a valence manifold. All this machinery has another advantage, is that it works in a straightforward way if the external potential is described by non-local pseudopotentials, which is typically the case. For ultra-short pseudopotentials, there are some additional terms that appear in the formalism, so it's somewhat more complex. And also, all this machinery works for monochromatic perturbations, the perturbations that have that appear as a periodic function times a wave vector factor exponential of I times a wave vector scalar product R. What happens is that linear response at linear order contains only terms with the same wave vector. So everything contains all response functions have the same periodicity, and the consequence of this is that there is no need to resort to supercell. So we can simply deal with the original periodicity and monochromatic perturbation, and without the need to introduce periodicity, to introduce a supercell, having wave vector Q as one of the reciprocal lattice vector. Now, the typical application for this machinery, for this approach, is the calculation of vibrational modes in molecules. Why? Because in the harmonic approximation, what we do is that we expand potential energy surface around an equilibrium set of equilibrium positions up to second order, and we obtain a harmonic Hamiltonian that can be transformed in an exact way into a sum of independent oscillators known as normal modes. So this is what the textbook says about vibrational properties. We have to write down. The matrix. We have to compute the matrix of interatomic force constants as a second derivative, that are second derivative of the energy with respect to nuclear positions, and to diagonalize it, to solve a circular equation in which this matrix of force constant is diagonalized with the mass matrix as overlap matrix. So it's a generalized eigenvalue problem. Actually, it's very simple because the mass matrix is diagonal It's a simple matrix, and so one can simply divide the dynamical matrix, the force constant matrix, with the square root of masses and obtain the the dynamical matrix that is directly diagonalized with conventional algorithms. Now, this is what is written above. What was written in the previous slide is valid for, let's say, finite systems. In crystals, we have that our quantum orbitals are characterized by a block vector K and the band index I, and atomic positions are labeled via their position in the cell, the basis of atoms defining the crystal, together with the lattice vector, so the position, which cell we are dealing with. We can write atomic positions as a lattice vector plus a vector for each type, for each atom. Now, it turns out that normal modes, which are called phonons in crystals, are also classified by block vector, by wave vector. They also have a mode index. Well, there are 3 times the number of atoms in the unit cell modes, or phonon modes. So instead of the matrix of the force constant, what we need is the Fourier transform of the same matrix of the force constant. So we just need those Fourier transform, and we get directly the phonon modes and the phonon energies at the given wave vector, Q. Now, how can we deal with that? Notice that we cannot compute directly the interatomic force constant in real space as defined in this equation at the bottom of the slide, because we cannot just, in a periodic crystal, you cannot displace a single atom, you cannot find the response to the displacement of a single atom in the entire crystal. It's not that simple. It breaks periodicity, and it's not a monochromatic perturbation. So we have to introduce a monochromatic perturbation, as shown in the definition here in the upper side of the slide. It can be shown that the object we need, that is the Fourier transform of the force constant at the given wave vector, are the second derivative of the energy with respect to such monochromatic perturbation that I have defined here as U of S as a function of Q. Now, these second derivatives can be computed knowing the linear response to the same perturbation. Then once it is computed, we can diagonalize the force constant matrix or the dynamical matrix and get the phonon modes. Now, just a few remarks. As I've mentioned before, no supercells are needed in this approach, unlike other approaches like the Frohnhoff-Olsen phonon, in which the monochromatic perturbation is explicitly built in with a small displacement. For the entire phonon spectrum, we need, for the entire phonon spectrum at the given wave vector, we need as many linear response calculations as number of atoms, as 3 times number of atoms there are, because there are basically 3 times the number of atoms in the unit cell, different perturbations, different lambda. So 3 polarization, 3 Cartesian direction, and displacement for each atom. And finally, notice that we are using, much in the spirit of the adiabatic approximation, the static response. So if we go back to the defining the original set of equations, here we have the static response. In the dynamic response would require the presence of an energy term here in the Green's function. But we assume that the response of electrons is so fast that you can neglect the effect of the energy of the motion of nuclei, of the fact that nuclei move with a finite frequency. Now, this answers the question how to compute at a given for a given wave vector, how to compute the linear response and the phonospectrum and the force constant in reciprocal space at a given wave vector, but doesn't tell us how to compute force constant in real space. Now, force constant in real space can be computed by inverse Fourier transform. That is, we compute in terms of force constant for a set of wave vector, a discrete grid of wave vectors. This discrete grid that is described in this slide typically is what it's a set of wave vector that spans the Brillouin zone, the first Brillouin zone. So it's a sort of reciprocal lattice with defining vectors, with the three defining basis vector G1, G2, G3 that are rescaled by some numbers, some discrete numbers, n1, n2, and 3, which means that the corresponding direct lattice vector is a supercell with length, with a size that is equal to the product of n1, n2, and 3. So we have a grid in reciprocal space of wave vector. The denser this grid that spans the Brillouin zone, the larger the real space, the corresponding real space grid. Which means that if we perform a sufficient number of wave of computation on this grid of wave vector, if our grid of wave vector is sufficiently dense, we can compute by Fourier transform, inverse Fourier transform, the force constant in real space on a supercell, and if the supercell of the original periodicity, if the supercell is large enough, since the real space force constant tend to decrease quite quickly with the distance, at least in non-porous semiconductors, simple semiconductors like the example that I'm going to show now, silicon and germanium. We have the interatomic force constant in real space, and then we can interpolate everywhere in the spectrum for whatever wave vector we need. We can interpolate, can easily recompute the phonons. Just a technical remark about symmetry. So it's useful when it's present. It's useful to use symmetry to reduce the number of calculations, in particular number of linear response calculations to be computed. So what is done, at least how it is implemented in Quantum Espresso right now, is that we select wave vectors, phonon wave vectors in the irreducible Brillouin zone. And then we symmetrize inside with the symmetry group, with respect to the symmetry group that leaves the wave vector of phonon wave vector Q unchanged. So this means that when we sum over block vectors of Kohn-Sham orbital K, we have to consider all K's that are in the irreducible Brillouin zone computed with respect to the subgroup that leaves the wave vector Q unchanged. It's a little bit confusing maybe, but basically you cannot use symmetry twice completely, both for wave vectors of phonon wave vectors and for block vectors of electrons. You have to use only once. Now, each linear response calculation costs more or less as much as a ground state calculation, no more than a few times what costs the ground state calculation. It's a considered ground state calculation. Apparently, it's easier to perform sort of self-consistent linear response calculation, but in practice, for various reasons, it may not be much faster. Actually, typically it isn't. Now, once we have our response in the irreducible, our force constant in the irreducible Brillouin zone, the wave vectors in the irreducible Brillouin zone, then we can apply symmetry again and obtain the entire force constant for wave vectors in the entire Brillouin zone. Now, this is what we get. These are quite old, from a quite old paper, one of the first successful applications of density function perturbation theory. Silicon and germanium are especially nice cases because even with LDA, actually, in particular with LDA, one gets very nice results for the phonon dispersions. Now, all this actually is true under an assumption. That is, the assumption is that the semiconductors are non-polar. That is, the vibrations, the phonons, have no associated macroscopic electric field in the limit of zero wave vector. But it is known from the textbook problem, it is known that this may happen actually in polar materials, so it's not even to doesn't have to look for strange cases. If you simply take silicon and germanium and consider the same lattice without with a different two sublattices with different atoms, so gallium arsenide instead of germanium, or what you get, or aluminum phosphide instead of silicon. Those cases are polar materials, and so the two sublattices are not the same, and there may be a macroscopic electric field in the U equals 0 limit of the wave vector. And this gives rise to something, to a phenomenon that is observable. It is called the LOTO splitting. So longitudinal optic, transverse optic splitting. The reason for this nomenclature, for this definition, is that what turns out is that the splitting is visible in optical modes, that is, those that have the two atoms of the sublattice vibrate one against the other, not in phase, but in opposite phase. And the splitting is present, the macroscopic electric field is present only in longitudinal optic modes, that is, those that have wave vector q in the same direction as the phonon polarization, that is, the phonon displacement is in the same direction as the wave vector q. Now, this is a problem because a macroscopic electric field is described by a potential which is clearly not compatible with periodic boundary conditions. It breaks periodic boundary conditions. So the potential associated to a macroscopic electric, this is uniform electric field, is as a form minus E electric field dot product with R, which is clearly not periodic. Now, the way to deal with such problem is actually known since many years, and is explained. It was first explained in a famous book by Borneo Wang, using the so-called long wavelength limit. Okay, how can this be explained in relatively simple terms? You have, in a way or another, you have to add your electric field as a separate variable and see under which circumstances this separate variable may appear. So we write a phenomenological expression for the energy, in which we have the energy as a function of displacement from the equilibrium. So U here are the displacement from the equilibrium, and that's this term here, the first term in this equation, is the quadratic term coming from force constant. That's quite normal, quite obvious. Then there is also a quadratic term coming from the presence of the electric field. The energy associated to an electric field is E squared, basically. We have to consider here the presence of screening from the electrons, and so we have to to put the electronic contribution to the dielectric tensor in the middle of the two electric fields, of the electric field here, of the square of the square of the electric field. And then there is the term that binds the two aspects, that is that relates electric field and atomic positions. And this is a tensor known as Born effective charge tensor. So this is the most general second order expression that you can build with displacements and electric fields. Now, one can do some electrostatic, in this case, and write down the so-called electric induction. So the field, screen the field into material. And in the limit, if one considers fields that go like with a wave vector q in the limit of zero wave vector, one finds that the electric induction D must be orthogonal to the wave vector, and that E, the scalar product, the vector product of Q with the electric field must be zero due to Maxwell equations. And this implies that the electric field must be longitudinal, that is, it must have the same direction as the wave vector Q. And then from this constraint on D and E, one finds that E can be written as a longitudinal field as in the second equation here in this slide, containing the displacement U and the Born charge, the Born effective charge Z star. And by some manipulation of the previous formula or previous expression of the energy as a function of atomic displacement, one put the electric field back here and gets that in terms of the atomic displacement only, the energy is quadratic, but the matrix of the quadratic form contains, in addition to the analytic term, that one that appears here that can be computed, is what we compute if we don't take into account the electric fields, microscopic electric fields. There is a term, an additional term, that has a non-analytic behavior, meaning that in the it may go to different limits or to different values for zero, the zero limit in the wave vector, the zero wave vector limit. So it's non-analytic, and it has to be included that to be added to the matrix of the force constant. So as far as we know, the Born effect dynamical charges, Z star, and the electronic contribution to the electric tensor, so we can compute this non-analytic term. So all we need are the Born effective charges. Now, the Born effective charges are also second derivatives of the energy with respect to an electric field and an atomic displacement. In fact, the effective charges are related to the polarization, electric polarization induced by lattice distortion, or equivalently, they are related to the force induced by an electric field in the system. The dielectric tensor is related to the polarization induced by an electric field, so it's also a second derivative. It's also related to a second derivative of the energy with respect to two electric fields. So we have a mixed second derivative for the effective charge and second derivative with respect to an electric field for the dielectric tensor. Now we have the problem. We have a problem. We encountered the problem I have mentioned before. That is, the perturbing potential representing a macroscopic electric field is not lattice periodic, which would be a problem that it can be actually solved is actually solved by the so-called modern theory of polarization, in which one may actually define the position operator in such a way that can be used as a lattice periodic operator in periodic boundary conditions. But there is a simpler, more straightforward way to deal with macroscopic electric fields, but in the linear response case, it is only if we consider linear response, by observing that what is ill-defined here is R matrix element of the position operator on the same state. So psi v, R psi v is defined. But what we need actually implicitly is the matrix element between an occupied and an empty state. So this matrix element can be recast into using psi c R psi v matrix element can be recast into an object that can be relatively easily computed by using by introducing an identity here. So by introducing the commutator of the Kohn-Sham Hamiltonian with the position operator R, and by dividing by 1 over epsilon c minus epsilon v. This holds, this is well defined as long as the two states are different. So, so one can use this identity here, the identity in the second formula here, to write the perturbing potential, the action of the perturbing potential over an orbital, a Kohn-Sham orbital, as in the third formula, exploiting the fact that this 1 over epsilon c minus epsilon v can be written again as can be transformed into a linear system in which the Hamiltonian, the Kohn-Sham Hamiltonian minus an eigenvalue appears. The commutator is well defined and it's relatively easy to compute. The commutator gives P, the momentum, apart from factors. And if there is a non-linear, non-local term in the Hamiltonian, it gives the commutator of the non-local term. So the commutator with the local potential is 0. Commutator of R with the local potential V of R is 0. With a non-local potential is not 0, but it can be computed. It's not difficult to compute. So once we have this term here, this equation, the third equation here, we can solve it, linear system. So we have the perturbing potential, and we can solve again we can either solve the linear response equations for the external field, or we can observe that what we actually need, the polarity, that is the effective charges, the polarization induced by an atomic displacement, can be written from the linear response to a displacement, to an atomic displacement, and the term, the bare term, bare potential, effective, the bare electric, the effect of the bare electric potential over a Kohn-Sham orbital. It can be written as a second, since it is a second derivative, a mixed derivative of the energy can be written by knowing this term here, this psi bar, defined in the previous, by the previous expression, the third formula in the previous in this slide, and by the linear response to an atomic displacement, or equivalently, it can be computed from the linear response of, the linear response to an electric field, and the derivative of the potential, the bare potential with respect to atomic positions. Again, by using the same trick of transforming the operator, the position operator, into its commutator with the Hamiltonian and solving a linear system, one can compute in the same way the response to an external field, and find the tensor, the electric constant tensor. Now, what happens is that the presence of this non-linear, non-analytic term in the force constant matrix has the consequence of making force constant, the determinant force constant, no longer short range. The implicit assumption that we've done in non-polar materials is that interatomic force constants have a short range, so there are no terms going far away, but it is no longer true if we have force constant in polar semiconductor due to this non-analytic term. And what we can do is simply to subtract out the non-analytic term. That is, we have to choose a term that has the same non-analytical behavior at Q equals 0 and that is easy to compute at finite wave vector. So we subtract out this term from the force constant matrices in reciprocal space. Of course, at Q equals 0, there is nothing to subtract out because it's not present at Q equals 0. But at finite Q, you have to remove this term in order to have an analytic and well-behaved behavior of the force constant at finite wave vector that once transformed back to from Fourier space to real space gives a short range force constant. Short range force constant matrix. So the procedure is basically the same, but you have to subtract out a term that has to be the same non-analytic behavior at Q equals 0, and of course it has to be when you recompute force constant in reciprocal space at the generic Q from the force constant in real space that you have just computed. In this way, you have to re-add the term that you have subtracted out when you have done the inverse Fourier transform. Of course, this means that the interatomic force constants are not do not contain the entire information. Some piece of information is contained in the function that we have subtracted out from the reciprocal space case. Something that should be remarked is that actually this discussion is not complete because there is also an additional term, additional quadrupolar term that may introduce non-analyticity in the force constant in reciprocal space. So this is something that is not yet present in quantum espresso. Here is relevant citation, the reference. Anyway, if one does the procedure as described, one finds also for polar semiconductor like gallium arsenide and aluminum arsenide, one finds some nice phonon dispersions. If one doesn't take into account macroscopic LOTO modes, macroscopic LOTO splitting, the LOTO splitting, one finds that here the result doesn't have the splitting here. At gamma you don't see the splitting in the optical modes between the LO and TO modes. So that is in fact not there for silicon and germanium. Gamma 3 optical modes are degenerate, while here 2 are degenerate and 1 is not. If you do phonon calculations in gallium arsenide and aluminum arsenide without taking into account that gamma equals 0, that Q equals 0, the microscopic electric field, you will find everything looks good except at gamma at Q equals 0, where you have wrong results. Now, what can one do in addition to once you have the phonon modes? Phonon modes, well, with the phonon modes and phonon displacement, the phonon frequencies, you can immediately compute something that is directly observable. That is, at Q equals 0, you have that with the effective charges and the phonon displacement pattern, you can compute the dipole induced by a phonon, the dipole induced by phonon dispersion, and this a phonon distortion, phonon displacement, and this dipole induced by a phonon squared is exactly what we need to compute the infrared intensity. It's proportional to the infrared intensity. That is infrared intensity that are a very useful technique to characterize materials. So you see phonons at Q equals 0, and it's very useful for characterization and for measurement. Another quantity that is less straightforward but very useful for studies are the electron-phonon interaction coefficients, because electron-phonon interaction coefficients are actually what do they need as basic quantity? They need the matrix elements of the linear response of the potential to displacement, to an atomic displacement, or to a phonon displacement, let's say. So the displacement, the linear response to a phonon displacement is implicitly computed. So what is computed actually is the linear response of the potential to a single displacement of an atom. But once you have the phonons, you can reconstruct from them the linear response to a phonon and compute the matrix elements, and then you can compute all kind of quantities related to the electron-phonon interaction coefficients. These are delicate calculations for reasons I will briefly mention soon. But anyway, the phonon code of quantum espresso is the basis for a lot of investigations on electron-phonon related properties, in particular using the EPW code that is part of the quantum espresso distribution. Something that is also interesting to know is that the ideas behind the density function perturbation theory, in particular the idea of getting rid of some of conduction bands and using instead the Sternheimer equation or a Sternheimer-like approach, can be extended to other cases, in particular can be extended to time-dependent density functional theory. There is in particular time-dependent density functional perturbation theory, whose basic reference is mentioned here, is written here, and also it can be useful. It can be useful for many-body perturbation theory, where this kind of perturbation sum appear, for instance, in GW calculations. So the idea can be recycled in several other important cases. But a few words about an electron-phonon interaction. The most typical application of electron-phonon interaction coefficient is the calculation of superconductivity temperature. One can use, for instance, the Macmillan formula. And what is needed basic ingredient apart the mu star, which is some parameters that can range around 0.12. It's a sort of effective parameter. It can also be computed, but it's maybe tricky. The difficult part is this lambda coefficient, nothing in common with the lambda at the beginning of this talk. It is a physical quantity, the electron-phonon interaction coefficient. And it's a sum of our wave vectors of a double sum at the Fermi energy of the electron-phonon interaction coefficients. It's something that can be computed directly in quantum espresso. It's a little bit tricky because this integral is very complex. It's very difficult to compute well. So you need a very dense grid of block vector scale. Otherwise, you can use the EPW. Finally, other quantities that can be computed using density function perturbation theory are all kind of thermal properties related to phonon vibrations. So in particular, the quasi-harmonic approximation in which you compute the phonon spectrum as a function of volume. And this gives you the free energy. And so by computing the phonon spectra at different volumes, you can have a good estimate of the vibrational free energy that is valid at temperatures that are not too high. Of course, it's an approximation. In the harmonic approximation, you don't have volume expansion, so the volume is fixed, volume expansion with temperature, so the volume will stay the same for at each state, irrespective of the temperature, which is not what happens, but by computing the correct phonon dispersion as a function of volume, you get most of the anharmonicity. You may account for most of the anharmonicity. And finally, it's also possible to compute non-resonant Raman intensities that are third derivative. They are related to third derivative of the electric constant or of the polarizability, electric polarizability respect the third derivative of the energy, that is a derivative of the polarizability of the electric polarizability respect to a phonon. So third derivative respect to a phonon and 2 times an electric field. This requires some finite differences. So you have to compute the electric tensor with a frozen phonon built in. Or otherwise, you may do that using second order response to electric field that is also implemented also with several restrictions, of course only for non-conservative operation. It has some restrictions. Now this is a list of basic references. The first 2 are The first 2 are basic references for this work, and the second 2 are references that describe some important aspects, more recent references only on some more important aspects. One is how to impose in a correct way acoustic thumb rule. Something I haven't talked about until now is that, in principle, acoustic modes at zero wave vectors should have zero frequency, exactly zero frequency. So for instance, at gamma here, Q equals 0, you have these three acoustic frequencies that have zero frequency. Now, there's something that is related to translational invariance. So it's not anything, it's not something very deep, it's simply related to the translational invariance. So acoustic modes at Q equals 0 are actually translated the entire crystal. So their frequency is necessarily 0. But if you compute, if you perform numerical calculations, these zero frequency seldom are 0. Actually, they are never 0. They are never 0 because there is a very small violation of acoustic some rule of translational invariance, more exactly, because what happens is that we are dealing with axial correlation, the axial correlation potential on a finite grid, real space and reciprocal space. And it's the grid that introduces a small breaking of translational invariance. Which means it's not a big problem as far as you manage to impose acoustic sound rules explicitly, and then you get again wave vectors zero at wave vectors and zero wave vectors. You get zero frequency, zero acoustic frequencies again. So you just impose explicitly the acoustic sound rule, but there are better and less good ways to impose the acoustic sound rules. In particular, if you have one-dimensional, two-dimensional materials, and so you have to be careful in how to impose those acoustic sound rules. And this is described in this paper. And another aspect is how to deal with two-dimensional cases. In the two-dimensional case, one has to notice that the LO-TO splitting vanishes. Now, in practice, what do you need to do in order to compute phonons in quantum espresso, or in whatever other code uses linear response techniques? But first of all, you start from self-consistent calculation at equilibrium positions. And this will compute the charge density and the Kohn-Sham orbitals, typically in the irreducible Brillouin zone for the symmetry group of the material. Then you may compute phonons, single phonons, that is at a single wave vector, or an entire dispersion. For the single phonon case, how does it work? Well, if you want to compute at a finite wave vector Q, non-zero, you just instruct the phonon code to compute for one wave vector, and what it will do a number of operations that are as follows. First of all, you need not only the Kohn-Sham orbitals at wave vector, at block vector k, but you also need them at block vector k plus q. If you look at the formalism, you will notice that you have a matrix elements of the perturbing potential, which has periodicity, which has a wave vector q between quantum orbitals, and which means that in a solid, two quantum orbitals must be labeled by the block vector k and the block vector k plus q. Otherwise, the matrix element is 0. So you need the code recomputes what it needs, and it also increases the Brillouin zone, the irreducible Brillouin zone. It has to be increased because typically there is just a subgroup of the original symmetry group that leaves the wave vector q unchanged. So the code first generates a number of additional quantum orbitals, then it computes, performs the linear response calculation. It computes the force constant at wave vector q and diagonalizes them, and then one gets the frequencies and phonon displacement patterns for the desired wave vector q. If you do the same at 0, you don't need to generate additional quantum orbital because you have all you need. You don't need to look at the symmetry that leaves 0 unchanged because it's already there. But what you need is, if you know that your system may have a macroscopic electric field at 0 wave vector, you have to specify that you want to compute the wave vector, the macroscopic electric fields as well. This will will perform additional linear response calculation for the macroscopic electric field, which basically will compute the linear response to an external electric field. And then from those results, it will compute the effective charges and the electoral part of the electric tensor. Then, in a separate code, you can impose the acoustic sum rule at q equals 0. You may add the LO-TO splitting and diagonalize the non-analytic wave vector, the force constant matrix with analytic and non-analytic terms inside. You have to specify, if you have non-analytic terms, you have to specify the direction of the wave vector. So q is equal to 0, but the direction along which you go to 0 is important. Sorry. For a complete phonon dispersion calculation, then you have to instruct the code to perform a number of calculations of an uniform grid of wave vectors. So you specify the uniform grid as exactly with the same logic that is used to specify the grid of block vector scale. In case your system is polar, you specify that you want macroscopic electric fields as well. So the q equals 0 calculation will include the calculation of macroscopic electric field. Notice that if you have a metallic system or something that the code thinks is metallic because you instruct it to treat the system as metallic, you cannot compute macroscopic electric fields because they don't exist in metals, they are screened. And so the code will complain. Then once you have made the entire phonon dispersion calculation, at that point there is an additional, a different utility that takes the set of computed matrix for force constant matrices for the various the grid of wave vectors and performs the Fourier transform to real space. For non-polar materials, it takes care to subtract out the non-analytic term. Once you have your force constant in real space, a final utility allows you to recompute at any given wave vector from wave vector you want to recompute the phonons by diagonalize the dynamical matrix. Here you have the definition of the diagonal matrix. So it's slightly confused because this last code is called MatDin, and the previous one that imposes acoustic sum rule and add the LOTO split is called DinMat. So don't mix up the two. Okay, I think I've finished now.
Thank you very much for the presentation. Are there any questions? Still have some time, so please, anybody?
I see one in a meeting in the chat. For the Born effective charge calculation in quantum espresso, is the symmetry used to reduce the number of linear response calculation? Yes and no. Example, only computing on irreducible atoms and applying symmetry operations for other atoms. Now, there are various ways to apply the symmetry in quantum espresso, in particular in the phonon code. Typically, what happens is if you compute the Born effective charge, you are implicitly exploiting the symmetry that is exploited for the phonons. So, the typical way to exploit the symmetry is by reducing both the grid of wave vector that you need, okay, which is not the case here because Born effective charges are Q equals 0, by reducing the summation of block vectors, K. So you are exploiting the symmetry there typically. So in your calculation where you sum over Kohn-Sham orbitals in the linear response calculation, you actually sum only on the irreducible, on K vectors that are in the irreducible Brillouin zone with respect to the symmetry of the entire crystal. So you are exploiting that. There might be other symmetries that might be useful, but they are not implemented because it's a little bit complex to implement symmetry things and so on, unless there is a valid reason. One tends to avoid. For instance, you don't really need to compute the response to electric field along all three directions. Typically, if you have a cubic system, you compute along one direction, you have all you need, basically. But this is not exploited. So the symmetry of that may be useful for the three to reduce the number of response to electric fields are not exploited. That is, you always compute three, you always perform three linear response calculations. Anyway, in the economy of a big calculation, three more calculation is not that much. Consider that you need 3 times the number of atoms calculations. You may, for a phonon dispersion, you may, under some circumstances, you may, for instance, if you have that your sum of a Brillouin zone is restricted to K equals 0, which happens for large cells. They happen for large cells. In that case, you may exploit the symmetry since you don't gain anything from reducing 0 to 0. It's always one key point, so symmetry wouldn't help in reducing the size of the calculation. In that case, you may exploit symmetry by computing linear response only for symmetry-independent atoms. There are some cases in which this can be useful. For instance, this is how, well, there is a specialized code that works only for zero wave vectors, uniform wave vectors, and zero block states, zero block vector. That works that way. In some cases, it's convenient. For instance, in cases like C60, many years ago, I made calculation for C60 and realized that the wisest way to exploit symmetry was to use it to perform calculations only for symmetry-independent atoms. There are 3 symmetry-independent atoms for cubic C60, so C60 in a cubic cell. Another question, not a metallic system. At the time, without using smearing, a single metallic atom doped semiconductor doesn't converge. In this case, is there any way we can use PHX at getting the ground state with smearing? A single metallic atom doped semiconducting system. Well, it depends whether the result after with smearing, sometimes you need smearing to converge even if it is not a metal. Then what do I do? In that case, what you can do is you converge with smearing, then you redo a calculation, restart from the result with smearing, and you redo the calculation without smearing, starting from the final charge density typically, and typically it should work. It should converge. Then you can perform a phonon calculation. One of these days, the first day, I have nothing else to, nothing more urgent to do. I'll think a way to convince the phonon code that if the input, if the starting calculation, the starting SCF calculation is not really for a metallic system, if the system is not really a metallic system, even if it is treated as metal, it may go on without complaining. Using starting wave function, starting pot, I tried it once, and if I remember correctly, charge is wrong, error. Well, charge is wrong means that it was wrong. Don't know. In that case, it's one has to look at the specific case in order to see what happens. Starting with, so one has to look at the specific case and how it was done.
Okay, so thank you very much for the questions, and thank you for the talk once again and for the answers. Now we should have a coffee break until 11, and at 11 we will start with the hands-on on phonons. So if there are no more questions, then we take the break now. Thank you very much. See you. I hope you had a nice break, and we will continue now with the hands-on on phonons. And I suppose Laura should take over now.
Okay, so Good morning, everybody. My name is Laura Bellentani. I'm an high-performance computing specialist at CINECA, and I've been involved into the porting on GPUs of Quantum Espresso, in particular Phonon. And today we are going to see some examples on what you can compute with Phonon, and also how you can run Phonon on GPUs efficiently. So, first of all, today we will cover some kind of calculation, in particular the computation of phonon modes and frequencies for a given Q point, phonon dispersion, and we will see also how to compute the Born-effective charges and the dielectric tensor. We will see these examples for both non-polar and polar materials, including LOTO splitting. Keep in mind that it is possible also to compute more systems and properties, for example, also magnetic system at the scalar relativistic collinear level, phonons for magnetic system in the fully relativistic non-collinear approach, and as a recent development, also phonon within the DFT plus U approach. So let's recap quickly the main physical quantity that is provided by the code. This is the matrix of interatomic force constant, which is defined, as you've seen this morning, as the second derivative of the total energy with respect to the atomic displacement. This is the definition in real space, and as you have seen previously, if you Fourier transform the atomic displacement, apply the Bloch theorem, basically those interatomic force constants can be computed independently for each Q point. So it is much more convenient computationally to to compute the interatomic force constants in the reciprocal space. These quantities are needed in order to define the dynamical matrix, which is diagonalized by the program in order to compute phonon modes and phonon frequencies. So let's start with the very first simulation of today. You can find this in the folder example 1A. In this case, we are computing the phonon frequencies at a single Q point, in particular the gamma point, for a non-polar material. Inside the folder example 1A, you will find, as usual, one README file which recaps the different steps that you have to implement for the phonon calculation, a job file where you can find all these batch options and the commands in order to run phonon on initially on CPU and then on GPUs in parallel. And a number of input files that you will need to submit with different executables to do the whole calculation, as we will see now, and also the pseudo potentials for the system simulated. So I will initially show the workflow, and then I will also show you from the command line how to run the example so that you can repeat the example by your own. So first of all, you always need to keep in mind that the simulation of phonon frequencies or dispersion is a workflow starting from the computation of the ground state wave function of the system. So before you need, at the very beginning of your simulation, you need to compute the ground state wave function of the system by using PWSL consistent. PWSL consistent will store these wave functions and charge densities inside an output directory. And this output directory is needed by phonon program in order to compute, firstly, the perturbed wave function for the Q point of interest. And from this, the force constant and dynamical matrix. And then the phonon frequencies for that Q point. Of course, this step, the perturbation of the ground state wave function, is a non-self-consistent step which is implemented inside, done inside the phonon program. It is inherited basically from the PW code, and it is done, of course, only if the Q point is not gamma point. So, the very first step for the simulation of phonon frequencies at the gamma point of this nonpolar material, silicon, is to implement a self-consistent calculation using PW. You have seen already how to run this kind of calculation. In this case, keep in mind that it is important that you preserve the output directory where indeed the wave functions are written, the wave function of the ground state. To run PW, I rewrote here the command line. We are working in a parallel environment, so you will find an MPI RAM launcher, but we will see that later in the terminal. Keep in mind that this is a relatively small system, so I suggest to run this simulation in parallel, but with not too many MPI tasks to avoid too expensive communications. So typically for this system, from 2 to 8 MPI tasks is a good number. Second step that you have to do is a phonon simulation. The input file for phonon contains some information. In particular, the name list is input pH, as you can see from the code snippet on the left. You need to specify the prefix of that you used to label the system for the PW self-consistent calculation. You need to specify the threshold for the convergence of the self-consistent loop implemented inside pH to compute the interatomic force constant, the dynamical matrix. And then you can also specify the atomic masses of the system. Remind that pH requires as an input also the name of the directory where you have stored the ground state wave functions from PW self-consistent. And then you need also to define with this file din the name of the file where you want to store the dynamical matrix for the point computed. After this name list, you will specify the coordinate, as done in the last line, the coordinates of the Q point in units of 2 pi over A. In this case, we are simulating phonon frequencies at gamma, so 0, 0, 0. The executable is called ph.x, and you can run it just by specifying as the name of the input file. In this case, ph.c.in. So, as we have anticipated during the lecture, basically, once we will do the simulation, we will see that the first 3 modes, the acoustic modes of the system, are non-zero. So this basically violates the acoustic sum rule. So what we have to do in this case, and this comes from the propagation of a numerical inaccuracy, what we have to do in this case is to impose the acoustic sum rule with an additional executable, which is called dmat.x, so that our, as you can see from the last step of this workflow, so that the phonon frequencies at the gamma point are the corrected ones. So, as we will see, basically, dmat requires its own input file, which is called c.dmat.in, This input file requires the name of the file where you stored the dynamical matrix, and also a definition of the asymmetric rule that you want to impose to the calculation. If you open the output file and check for the phonon frequencies, you will see that in this case, the first 3 acoustic modes have now 0 frequency. So the correction is imposed by DIMAT. Okay, let's see this now from the terminal so that you can repeat this example. So here we are inside the folder P3. The README shows the different the content of the different folders. Inside example 1A, you will initially, as you can see, run the PW simulation. You can decide if you want, you can work in interactive mode and just run by command line, launch by command line the PW, pH, DMAT calculation. Otherwise, you can submit the job. In the job, you find already set the account name and the reservation name for today. Remind, if you use the interactive mode, that the reservation name is different from the one you used the other days. You can use the Quantum Espresso installed by yourself, or you can rely on a Quantum Espresso module installed on the cluster, as I did for this exercise. So here you can see I run, let me just, so here if you want to review, you can see the input of the ground state calculation. Now we submit the job. I hope, okay, the reservation is correct. So we see that the code is running. The output is written inside pw.c.out. The convergence is very fast. The system is small, so it is very fast also with just 2 MPI tasks. And now you can see that there is a directory out which contains the ground state wave function. Now, if we look inside pH, we check that the name of the output directory coincides with the name, so the name of the input-output directory of pH is the same name of the input-output directory of phonon of PW consistent. And then we can submit also, we can submit also the other job, which will run on the compute nodes pH with 2 MPI tasks as well. So let's submit pH. It is running. We can inspect the log file. So as you can see, basically the code is reading the saved data from the output directory. It is calculating the phonon frequencies at the Q equal to 0, 0, 0. And as you can see, basically the code, the log file, tells you that the dynamical matrix for this Q point is computed by using 2 irreducible representations. So as you can see, the code implements 2 separated loops up to convergence, one for each irreducible representation. Once the 2 contributions to the dynamical matrix have been computed, the dynamical matrix is diagonalized in order to compute the phonon frequencies. So the phonon frequencies can be found in the log file, but also in the c.din file here. In this file, you will see for the given Q point, the phonon mode and phonon frequencies. Now, as I anticipated, the first 3 acoustic modes are not 0. So what we should do is to impose the acoustic sum rule with the DMAT program. You can launch DMAT with the SRAN or MPI run launcher, but the DMAT is not distributed with RNG. So basically, you can just launch with an MPI task. I just review the input. Here we specify the name of the dynamical matrix because DMAT does not read the output directory, but reads c.din. Okay, fine. So if we submit the last step, okay, we see this calculation is very fast. It should take like less than 1 second. And then now, if we look at the file DMAT.out, we see that the frequencies are corrected with the acoustic sum rule imposed. Okay, so in addition to the DMAT.out, you can also find a DMAT.ixsf if you want to compute the phonon modes with XCRIS10. So now I would leave you 10 minutes to repeat this example, and then we will see how to compute phonon dispersion for nonpolar material. So I will be available for breakout room if you want. And if you write in the HMD, I will stop sharing. Allora. How to stop sharing, I don't know.
You did.
I stopped sharing, okay.
Yes.
Okay, so I will be available for questions on HMD, breakout room. I think that at 30 past 11, we can resume and do the second part. Okay, so I see that you are running the example one. Let me share again the screen. So let's go here. Okay, so now we saw how to run a phonon calculation for frequencies at a single Q point. Let's now see how to compute a phonon dispersion. So you saw during the lecture that it can be more convenient to compute for phonon dispersion the interatomic interacting for constants by using Fourier transform and interpolation. Let's see how phonon, which is the workflow that you need in order to do it with phonon code. This example is provided in the folder example 1b. Here you see that there is a larger number of input files because the workflow requires more steps. So the very first step is always a ground state calculation in order to implement it with the PW self-consistent. The second step is a phonon simulation. In this case, you need to inform the program in the input file that you want to compute a phonon dispersion. And you need also to define the uniform grid of Q points for which the program starts the calculation of the phonon dispersion. So in this case, in the input file, you specify LD is equal true, and then you specify a number of Q points in the three directions in order to build a dense enough grid of Q point. For example, for this system, we specify a grid of 4 times 4 times 4 Q point for a total of 64. The program will not compute the dynamical matrices for all these 64 Q points, but it will reduce the calculation to the computation of the dynamical matrix for some non-equivalent, for the non-equivalent Q points according to the symmetry of the system. In this case, for this system, in particular, the number is 8. If you do this kind of simulation, you will see indeed that the number of c.din file given as an output is 8, from 1 to 8, one file for each dynamical matrix of a given Q point, non-equivalent Q point, together with a sin.din0, which contains the whole list of the non-equivalent Q point for that grid. Now, once we have these dynamical matrices, you can apply the Q2R program in order to do a Fourier transform from the reciprocal to the real space. This will compute the EFCs in the real space. Now, the input file requires to specify the name of the file where you stored the dynamical matrices, the asymmetric rule that you want to impose, and also the name of the file that where you will store the EFC in the real space. Okay. So once we have interacting for constants in real space, we can implement a Fourier interpolation in order to compute the phonon dispersion, in order to compute the interacting for constant at first at any Q point, even if this Q point is not initially contained in the grid, say defined, used in the grid that we have initially, for which we have initially computed the dynamical matrices. The name of the executable which does this operation is matdin, and the input should specify the acoustic sum rule that you want to impose, the atomic masses, the name of the file where you stored the interacting for constant in real space, and the name of the file, in this case c.frec, where you want to store the dispersion. Below the name list, you should set the number of Q point for which you want to compute the dispersion, and then the list of the Q point in Cartesian coordinates. Once you obtain as an output this c.frec file with the phonon dispersion, you can plot it by using a post-processing code which is provided by phonon, and this post-processing executable is called plotband.x. Inside the plotband.c.in, you find the values that you can put as an input in order to provide the phonon dispersion. So, of course, this phonon dispersion is calculated by using Fourier interpolation. So, if you want to check that your calculation is accurate enough, you can compare this phonon dispersion with a phonon dispersion computed with a different grid, let's say a less dense grid. And if you see that basically the two phonon dispersions overlap quite well, your calculation, so your choice of the grid of Q point is dense enough for the system. Or you can try to overlap the phonon dispersion computed with this approach with the phonon frequencies computed with the exact method, with the first method for some selected Q points. So actually, MADIN can also be used to compute the density of state. Check, please, in the user guide for the input how to do that. This would require an additional parameter, DOS equal true. And keep in mind that the Fourier interpolation works very well if the Q points is dense enough and does not work very well if the EFSEs are long range. In particular, this is not the case for Cohen anomalies in metal or polar insulator. For the polar insulator, in particular, there is a non-analytical contribution which is added to the analytical one in the reciprocal space, but this additional term, as we will see later, can be dealt with effective charges and the electric tensor. So, briefly, let's see how to run this in example 1b. So, first of all, we need, well, to submit the PW cell consistent. Once the output directory, so once the ground state wave functions are computed, we can also, in this case, keep in mind that we want LDisp equal true for the phonon dispersion, and we want to set the number of Q point. For this system, small system, 444 is enough, but you can also modify this. Then we submit the job. If we inspect the output, we will see that now, here at the very beginning, the log file tells us that it is computing the dynamical matrices for a uniform grid of Q point 444 in each direction, which corresponds to 8 non-equivalent Q point. And for each one of these Q point, basically it will do here. This is okay. This will take a little bit longer because for each Q point, it will compute the dynamical matrix one by one. For example, this is the first Q point with the two irreducible representations, and then it diagonalizes the dynamical matrix in order to compute the phonon frequencies, and then it will repeat the same calculation for the second Q point, which has a different number of irreducible representation, and so on, up to computing the diagonal matrices for all the Q points. Then we need, as we have seen, to use Q2R in order to compute the to Fourier transform in the real space. So I think the simulation on phonon, okay, this is done. Also, Q2R can be launched with just one task because it's compiled for MPI, but it's not distributed. This simulation should be very fast. Okay, this is done. This generates this file containing the interacting for constant in real space. And then with the last step, we can compute apply the Fourier interpolation and compute the phonon dispersion. As an input here, martin.c.in, remind to specify the name of the file from which these parameters are read. Sorry. Okay. After this last step, you will obtain the c.frac, sorry, I don't remember the name. See, the c.frac file, and inside the folder you can also find a new plot file to be used, that you can use directly to compute to plot the phonon dispersion with nuplot. To use it, module load nuplot. Sorry, you should also use plotband.x. Okay. I will leave you, let's say, 7 minutes just to reproduce the example and see if you can get the band dispersion. And then we will back for the next exercise. Okay, I'll reply to the question in the chat. Oh, sorry. So it's an executable plotband.x. Once you generate once you implement this step, which is the add-in step, this will store the dispersion in a file called c.frac. Then you just run like this. Sorry, let me. That's like this.
You should share the screen.
Sorry. You're right. Okay, here we are. So now this is the content of plotband.c.in. Let me load the Quantum Espresso module. There is an executable for post-processing called plotband.x. If you provide as an input the name of the input file, and then the other parameters, frac.plot should be, yes, the name of the file. So, okay, I just put in the input values. Then, and you open plot dispersion.gp. This basically is a GNU plot file that you can load with GNU plot and to plot fric.plot. Okay. Now I will remove this terminal, so maybe we can see it also from here. Want to load the new plot. We can load plot dispersion. No, sorry. Let's go to new plot. Then load the plot dispersion. And then you should see the dispersion. Okay, here. Okay. So yeah, you should do the step for the post-processing in order to get the frac.plot.
Can I have a question?
Yes.
There is a file which called se.frac.gp, which is already, there is the data in it, if you see it. And you can plot it with the GNU plot, and that's all.
Yes, this is another way to do the step. I mean, to do the plotting. But for example, in this case, you can also modify.
Yes, this is why I wrote in the chat.
Ah, okay, okay. Okay, so I see that you are doing the exercise. You got the phonon dispersion. So now we can see how to do the same similar exercises, but for polar materials. At this point, let's start with the calculation of phonon frequencies at gamma. In a polar material, we need to take into account this non-analytical term that arise in the interatomic force constant at Q at gamma. In particular, near gamma, in particular, this term, as you can see, can be computed if we know the effective charges and the electric field. Phonon provides the pH code, provides indeed also these quantities if you specify this in the input. So, of course, also for this example, we need to start with the ground state calculation, and then you need to do the second step. But at this time, you need to specify also that you want to compute the effective charges. To do that, to compute the effective charges and the electric tensor, you need to specify epsilon equal true. This will automatically compute also the effective charges. The computation at this point will provide also these two additional quantities before the calculation of the dynamical matrices inside the output provided by pH. Now, if we look at the output and the dynamical metric, the phonon frequency, sorry, you can see that in addition to the acoustic sum rule, we also need to impose the LOTO splitting, which is not included, which is not present in our calculation. So this is managed by the DMAT code, which can add, together with the acoustic sum rule, the LOTO splitting. In this case, you need to specify, together with the acoustic sum rule, the name of the file for dynamical metrics and atomic masses, also the direction for the LOTO splitting. Then, if you repeat, so if you submit the calculation of with DMAT and you check for the phonon frequencies, you will see that the LOTO splitting is applied together with the acoustic sum rule. Okay, so this example is very similar to the previous one, so I will also show how to compute, well, I will just recap how to compute phonon dispersion for polar material, and then you can decide which exercise you want to do, or you can do both, as you wish. The phonon dispersion for the example for phonon dispersion in polar material can be found inside this directory. Here, you need basically to repeat the different stages. Here there is an issue with the index, sorry. The 4 stages for the calculation of the phonon dispersion, starting from the ground state calculation of the system to the computation of the dynamical matrices for a uniform grid, a suitable grid of Q points, and then you Fourier transform the interatomic force constant in the space. The non-analytical terms are automatically managed by the program, as you've seen during the lecture before. and then you need to apply an interpolation to compute the phonon dispersion for a grid of Q point. You can, in this example, basically you will find the job file, the input file. Inside the input file, there are some missing parameters, so that you have to add by yourself in order to compute the phonon dispersion. So you can decide if you want to do the previous exercise or this exercise or both. But if you do this exercise, just check carefully the input file, because there might be some missing parameters that you have to fix. If you compute the phonon dispersion, then you will see that the phonon dispersion has the LTO splitting in polar material. Okay, so I will give you 10 minutes for this exercise, or one of the two or both, and then we will see a little bit. There is another exercise about 2D materials. This at the end is not so different. We don't have the time to see it today, but it's not so different from the phonon dispersion of polar and non-polar material. So if you want to do it. And then we will see a little bit on how to run phonon on GPUs efficiently, and which parallelization levels you could use to exploit GPUs. So let's be back with the last part, with the last exercises at 10 past 12. Did you hear me?
Yeah.
Okay, sorry, because my microphone was muted, but apparently not really. Okay, so also this exercise basically was very guided, and you should be able to reproduce the phonon dispersion or phonon frequencies as we did for the first two. Now let's see how you can run phonon on GPUs. This is just a nice plot that shows basically that the phonon code, most of the driver of the phonon code, PHQSCF, runs on GPUs, which you can see with this blue activity on the GPU, which refers to kernel computation. If you want to build Quantum Espresso for GPUs, you can find here the instruction for Barbora. And for this exercise, inside the submit file, you will use the submit file basically will use a binary installed in our work area using the same software stack. But if you want to reproduce the install, you can also try yourself. Of course, remind that you have to specify where to find the source code here in add SRC with the path to the source code. You can add the path of the Quantum Espresso that you downloaded the first day. And you should be able to compile also login node. Okay, with this script. So one important thing to highlight when you want to run Quantum Espresso on GPUs, in particular phonon, is that with the GPUs, you can use in Quantum Espresso MPI together with GPUs. And in this case, usually the most efficient configuration is one MPI task per GPU. So indeed, in the examples that we will see today, we have 4 GPUs per node on Barbora, and we will launch one MPI task per GPU. Okay, each MPI task will offload its computation to one of the 4 available devices on the node. It is important to keep in mind that you can exploit, according to the program, the different kind of the different parallelization levels that are available in Quantum Espresso. The default one, however, RNG, is very efficient on the CPU, but on the GPU, it entails communications, many communication, and these are very costly for GPU computing. So unless you have some memory constraint, try avoiding the use of RNG, so the default one. With GPUs is more efficient to use pool, so try distributing computation over different K points by using pools. Pools are activated by a command line argument -nk. In Phonon, there is a restriction on the number of pools that you can use. In general, the number, of course, for a gamma calculation, a calculation at the gamma point, the number of pool is at maximum equal to the number of K point. While unless the calculation is a non-collinear or magnetic system, where due to some, let's say, to spare some computation, basically, each pool can compute at minimum 2 K points. So the maximum number of pool is equal to the maximum number of K points divided by 2. If the calculation is not a gamma calculation, a gamma calculation at the gamma point, then the maximum number of pool is equal to the number of K point divided by 2, unless it is non-collinear or magnetic system, where this is the maximum number of pool is equal to the maximum number of K point divided by 4. So, of course, using pools is very efficient because it entails little communication, but there is this limit that you have to keep in mind on the maximum number of pools that you can use. In Phonon, you can also exploit images. Images are an MPI group that handles calculation on quantities that are totally independent. In particular, for the kind A of the exercises that we've seen today, so calculation of phonon frequencies at a given Q point, you can use images to distribute the computation on different irreducible representation. While for phonon dispersion, you can use images to distribute the computation on different Q points, because the computation of the dynamical matrices for the different Q points is totally independent. As well as in the first case, in the case of computation of the dynamical matrix for a given Q point, it is possible to split this calculation into independent calculation on the different irreducible representations. When you combine pool and images, you can achieve a very good performance and scaling. This is, for example, the comparison between the time to solution on Galileo 100 and on Leonardo for a CPU versus a GPU run. So you see that the speed up for this system that we have recently benchmarked is from 10 to 7. So it's a very good speed up. And combining pools together with images, you can scale up to very, very large scale. For example, here we scaled the simulation up to 1024 GPUs on Leonardo, which is about 1/3 of the whole cluster. But let's see a little bit more into detail what this distribution on GPUs does. So inside I will show you directly from here. Inside the day3 folder, you will find the simulation of another system. In this kind of simulation, the one in example 4 is a phonon frequency calculation at the gamma point. if you open pH, indeed, you will see that here we are asking to the code to compute phonon frequencies at the gamma point. So you can do the typical workflow for this kind of simulation, but now we want to exploit pool distribution on GPUs. This is done, for example, in example 4a, or in example 4b, we can exploit image distribution. Sorry, the exercise here is already done, but basically you will find only the input and the submit file in your directories. So the execution is very similar. You only have to keep in mind, let's go, for example, to the phonon code, that now we have, as I said, I suggest to run 1 MPI per GPU. You have up to 4 GPUs on a single node. And so, for example, here I decided to use 2 GPUs. I submit my job. And in this case, sorry, I want to submit my job, but I want to parallelize over pools. So, in particular, I want to use 2 pools. So I launch the simulation with -nk equal to 2. If I submit the job and I look at the output, here for convenience, I store the output inside a file named out.0.0. What I see here, first of all, is that I'm using 2 pools to distribute K point. My system has 20 K point, so of course I would expect that the first pool handles the calculation for the first 10 K point, and the second pool for the remaining 10 K points. And this is, and then, of course, at the end of the simulation, I can compare, for example, how much I gained with respect to launching on a single pool or on the CPU. But this kind of simulation will basically provide directly the dynamical matrix. Of course, this dynamical matrix is affected by the non-zero acoustic modes, and to correct this, we should impose with DMAT the acoustic sum rule. So running on pools is not so different, does not require additional steps. It just requires to specify that you want to use 2 pools. Please do not activate RNG, so use a total number of MPI tasks equivalent to the total number of pools, because otherwise the communications will make the computation longer. So this system is not big enough to use RNG efficiently. So just use a number of MPI tasks which is equivalent to the number of pools. Then in this other folder, you can try running on GPUs, but in this case, you can exploit images. To do that, the system is always the same. We are calculating the phonon frequencies at the point gamma, but I want to run 4 images, use 4 images. So I need to specify as an argument of the executable -ni4. Once I submit this job, this will generate this out.star file. Okay. Sorry, let's check before what happens if I don't use images, like in the normal case, or here. If you check there are, if you look for there are, you can see that this system has 5 irreducible representation. So now I can, of course, use up to 4 images, because this system, basically, this simulation is doing one self-consistent run up to convergence for each irreducible representation independently. So if I run the simulation as done here, distributed on images, each image will handle a subset of the irreducible representations, and each image will write its own log file with all the information regarding its computation. This kind of calculation, irreducible representation, are very independent. The amount of communication is the minimum. They only communicate at the end by weighting each other. So, for example, if we look at the log file of the image 0, we can see here at the beginning that the log file tells you that there are 5 irreducible representations. This image, which is image 0, does representation 1. Okay? If we look at out.1, which is the output file, the log file for the second image, we can see that the next message, that there are 5 irreducible representations, but this image will do the representation 2, and so on. Okay, so I invite you to try either the pool or the image workflow. I mean, at least to submit the PH file up to step 2. This might take a little bit longer, and then we are a little bit late, but I think I can finish 10 minutes later with respect to what we prevented. And then we resume and we have a look to the output just for a few information regarding how to complete the run and which are the performances in this case for the image simulation. Okay, so you can decide if you want to do example for A or for B, and submit the job and see the log file for the runs on GPUs. We will resume at 35.
Laura, we cannot hear you if you're talking.
Indeed, I was talking, sorry.
Yes.
Okay, thank you. Okay, so sorry, it was just a recap. Okay, in example for A, basically you can find the solution for pools. Here the output is not very different from the one that you run on CPU or serially. Basically, you will end up having the dynamical matrix, the phonon frequencies in just one run. While if you run on images, now you see that, sorry, example B, images, you will have 4 different log files referring to what each image does. Images implement independent calculation. Each image will compute its own contribution to the dynamical matrix according to the irreducible representations that has. And if you look at the end of each log file, if you check, you will not find the dynamical matrix. Sorry, you will not find the phonon frequencies here, because this step, when you distribute on images, is not enough to compute the phonon frequencies. This step computes only the dynamical matrices independently. Indeed, inside out, you see that each image has its own directory, and inside each one of these directories, there is an XML file which stores its contribution to the dynamical matrix for that Q point. Indeed, this first index states for the Q point. Here we are computing only one Q point, so Q point number 1, which is 0, 0, 0, and 2 refers instead to the irreducible representation. Okay, so all these contributions to the dynamical matrices needs to be aggregated, and then the dynamical matrix needs to be diagonalized in order to compute the phonon frequencies. How to do that? There is a third step that you need to do. This is a very fast step compared to the previous one. Just you need to run the the simulation by using ph.recover.in by using the input parameter recover equal true. Okay, once the simulation is done, you need to recover the simulation. But you need to run with one image only. So you need to recover the simulation after all the contribution to the dynamical matrices are computed with one image only. So let's submit this third step. Okay, it will take some time. Okay, it's very fast, and this step will actually diagonalize the dynamical matrix and compute the phonon frequencies. Then you can apply LOTO splitting, acoustic sum rule with the other executables. But keep in mind that when you distribute by images, you need to add this step, a recover run with one image only. Keep also in mind, now let's check the time taken by each image. So this is the time taken by the first 4 images. Let's do this. Okay, now you see that the first 3 images take about 1 minute and 20 seconds, and the last image 2 minutes and 10 seconds. Now we have 5 irreducible representations, and we are using 4 images. So of course, one irreducible representation will have to compute the contribution to the dynamical matrix for one image has to compute the contribution to the dynamical matrix for one irreducible representation more with respect to the other images. So of course, this is the slowest image, and actually, and the hold time for the slowest image is the one that dominates the overall hold time of my program execution, because here in each log file you find the time taken by each image to compute this contribution to the dynamical matrix, but the program actually ends only when the simulation is over, so only when all the images have finished their own work. So this is important because, let me show you some, because even if this is the time taken by the different images according to different parameter configuration, where we are distributing with a different number of images and pools. And you can see that in some configuration, even if some images take less time to finish their calculation, the slowest image is the one that determines the total hold time. So eventually, you need to balance the number of pools and images in order to achieve the best configuration with the lowest time to solution. Okay. So generally, if you want to exploit efficiently GPUs, keep in mind that you need to prioritize image and pool distribution according to the system, if those are available. Try to ensure that the workload is balanced among the MPI processes. Keep in mind that you can use RNG, the default parallelization level, but the efficiency is limited, especially if you try to scale, use RNG beyond the single node. And for the ones who are more into GPU computing, GPU programming, try to use, if you are installing by yourself the Quantum Espresso version, try to use the GPU-aware version of the code of course, if the cluster supports GPU direct communication. GPU awareness is activated by this flag. Okay, so I thank you for your attention and also for the support of all the other tutors and professors for the question and answers. And I will leave the floor for the conclusion.
So I would like to thank all our speakers. Many of them are still here with us. So thank you very much for the great lectures and for the hands-on. It was very busy 3 days, and I hope our participants have learned a lot from you. And I think I can say that the MaX Center of Excellence is there. It's not, it's a long-lasting Center of Excellence. So if you have any questions regarding Quantum Espresso, or if you would like to learn more or repeat the course, there's always a chance. So you can check the MaX COE website and get in touch with all these experts. So thank you. And also from my side, thank you for the collaboration, because it was really smooth and easy going for us. And thanks to our participants for being with us for 2.5 days. It was amazing. So thank you also for being interactive. Thank you.